Assalamu alaikum everyone. I hope all of you are doing well. We will start work, power and energy today. We will start from basic definition of work done. If you apply any force at any body, for example, if this is a body and you apply a force F at this body and this body covers some distance d in the direction of force after the application of force, then the product of force and the distance covered in the direction of force is called work done. And it is measured in joules. The system international unit of work done is joules. You can see in this diagram that the direction of force and the direction of distance covered in the direction of force is same. The direction of both quantities is same. But sometimes there will be an angle between force and displacement. Let's suppose if this body is being pulled by this force F, like this. This body is being pulled by this force F, and the line of force is making an angle theta with the horizontal axis. And let's suppose this body covers this distance d till this point. Okay. Now in this diagram you can see that there is an angle between force and displacement. So what will be the expression for work done in this case? We can resolve this force into components. This will be the horizontal component and this is called F cos theta. And this is the vertical component. This is called F sin theta. And we know that this body is moving horizontally. It is not going vertically upward. So only horizontal component of force is active. This is inactive. This component is inactive. So the component of force which is along the covered distance is F cos theta, this component. So if you multiply force and distance, in this case only horizontal component is active. So the force will be equal to F cos theta. So at the end we will have this expression for work done. W will be equal to Ft cos theta. So if the direction of force and displacement is same, we will be using this expression, and if there is an angle between force and displacement, we will be using this expression. After this we have power. It is basically work done divided by time, or the rate of change of work. This is the expression for power, and its system international unit is watt. But if you see the formula, we know that the unit of work done is joules and the unit of time is second. So joules per second is equal to watt. For example, we can write that 1 watt is basically equal to 1 joules per second. Similarly, 6 watt is equal to 6 joules per second. If power of any body is 6 watt, it means that this type of body is consuming 6 joules energy in 1 second. Similarly, if power of a body is 10 watt, it means this type of body is consuming 10 joules energy per second. Okay. After this, we have energy. It is basically the ability to do work. You know that we have two types of energy: kinetic energy and potential energy. This type of energy, kinetic energy, it is energy due to velocity or due to movement. If a body is moving, the moving body will have this type of energy, which is called kinetic energy. And this energy, potential energy, it is basically the energy due to position of a body. We have some expressions for these two energies. Kinetic energy is equal to 1 over 2 mv square, half mv square, and potential energy is basically equal to mgh. We can see in this formula that kinetic energy is depending upon velocity, because 1 over 2 is constant, mass is also constant. So kinetic energy depends upon velocity, and potential energy depends upon the height. If height of a body is 0, it means this type of body has 0 potential energy. Similarly, if a body is at rest, it means the velocity is 0, and if velocity is 0, the body which is at rest, it will have 0 kinetic energy. And look at this diagram. Look at this diagram. Let's suppose a body of mass m is released from this point and it comes here at this point. Okay, now the distance between horizontal line and this horizontal line is h. At this point, because height is maximum at this point, so potential energy will be maximum at this point. And let's suppose that this body is at rest at this point, so here kinetic energy will be 0 because velocity is 0 at this point. And if you release this body from this point, and if this body hits the ground, just before hitting the ground, this body will have maximum velocity. So just before hitting the ground, this body will have maximum kinetic energy, and potential energy will become 0 because just before hitting the ground, the height is almost 0. So potential energy will be 0 at this point. Now what is happening here? That the potential energy at this point is converting into the kinetic energy. So the entire kinetic energy of this body at this point is coming from the potential energy that this body had at this point. So we can see that potential energy and kinetic energy are converting, and both the dependence of both energy, that potential energy basically depends upon height and kinetic energy depends upon velocity. And we can find change in kinetic energy and change in potential energy. For example, if initial velocity of a body is u and final velocity is b, the change in kinetic energy will be equal to the 1 over 2 mv square minus u square. This is an expression for change in kinetic energy, where u is initial velocity and v is final velocity. And similarly, we can have an expression for change in potential energy that will be equal to mg h2 minus h1. h1 is initial height and h2 is final height. This will give us the change in potential energy. And after this, we have a very, very important definition, which is called the work energy principle. Work energy principle. Basically, whenever a body has some energy, it is always coming from a work done. For example, if I am pulling this body, if I apply a force F at this body, definitely this body will cover some distance and this body will start moving. Okay, and let's suppose this body comes here after the application of force. Now at this point, this body will have some type of kinetic energy because this body is moving. Okay, now this body is moving because of the application of this force. Actually, this force F is doing some work done at this body. It has some work done at this body, and the work done by this force F is converting into the kinetic energy. So, if let's suppose if I throw this marker like this, then actually I am doing work at this marker, and the work which that I am doing at this marker is converting into its kinetic energy. The kinetic energy in this marker, if this marker is moving, the kinetic energy in this marker is coming from the work which I have done at this marker. So basically, work and energy are same thing, and both things are measured in same unit. The unit of work done is also joules, and the unit of energy is also joules. And we can have a very, very important equation which is useful for the solution of examples. This is work done by driving force is basically equal to change in kinetic energy plus change in potential energy plus work done against friction. We will be using this equation in our upcoming examples. Okay, now let's start an example. We have an example for we will be utilizing these concepts in this example. Okay, this is a horizontal surface AC and a body is released from this point O, and the distance between this point O and this point A is 2.4 meters, and this surface, this inclined surface OA, is making an angle of 50 degrees with this horizontal surface, and we have another point C at the same level of A, because this is a straight line, AC is a straight line, and a particle P whose mass is 0.8 kg is released from point O. We are supposed to find kinetic energy of this particle P at point A. Okay, now let's start with the solution of part 1. Okay, let's start with the solution of this part 1. We are supposed to find kinetic energy at this point A. We know that kinetic energy can be calculated by using this expression. Kinetic energy is equal to half mv square, but we don't have velocity. We don't have velocity of this particle B, so we won't be able to use this formula. What we are going to do, we can calculate potential energy of this particle at point O. The potential energy of this particle at point O will be converting into the kinetic energy at point A. So when we calculate the potential energy at point O, we will be using same value for the calculation of kinetic energy. Okay, so if we use the trigonometric identity, we know that this is H. We know that in this triangle, sine 50 will be equal to H over 2.4. If we apply this trigonometric identity at this diagram, we will have H equal to, let's calculate this, H will be equal to 1.83. H will be equal to 1.83 meters. Okay, now it's 2.4 sine 50. Okay, this will be equal to 1.83. So the potential energy of this particle at point O will be equal to mgh. At this point O, the potential energy of this particle will be equal to this expression, and the mass of the particle is 0.8. The gravitational acceleration is always 10, you know this, and this will be equal to 1.83. If we multiply these three quantities, we will have 14.7 joules. Okay, now this is basically the potential energy at this point O, and same potential energy, the potential energy of this particle P at point O will be converting into the kinetic energy at point A. So at point A, this potential energy will be equal to the kinetic energy, and so potential energy at point O will be equal to the kinetic energy at point A. At this point, we know that this is basically equal to 14.7, and kinetic energy is equal to 14.7 joules. Kinetic energy at point A will be equal to 14.7 joules. Okay, now we are supposed to find, in second part, we are supposed to find the speed of this particle at point C. Okay. Now, if we follow work energy principle, we know that the kinetic energy of point A will be equal to the potential energy at point B. Plus, we can see that the distance between A and B and B and C is equal. So, the kinetic energy at point A will be equal to the kinetic energy at point C. Because this kinetic energy will convert into potential energy at point B. At point B, and the kinetic energy of this particle B will be maximum at point B. And when this particle will come at point C, at this point C, the kinetic energy of this particle will be equal to the kinetic energy of particle B at point A. So we can write that the kinetic energy of point C at point C will be equal to the kinetic energy at point A. Okay, and we know that at point A it is basically equal to 14.7, and the formula of kinetic energy is half mv square. Vc is the speed of particle at point C. Okay, and we know that mass of this particle is 0.8. So if we simplify this, we will have 14.7 multiplied by 2 divided by 0.8. So we will have the speed at this point C, it will be equal to 6.06 meters per second. Okay, now look at part 3. We need to find the vertical distance of B from the line AC. We need to find this vertical distance, this. And it is given that the greatest speed of P is 8 meters per second. Okay, we know that if we release this particle from point A, then coming to this point, the kinetic energy of this particle will increase, because from point A to point B, velocity of this body is increasing. So kinetic energy of the particle P from point A to point B will increase due to increasing speed. And if kinetic energy is increasing, then there will be a loss in potential energy, because height is decreasing. At point O, height is maximum, and at point A there is a slight change in height, and at point B there will be a difference of height from point O. So for the motion of this particle P from point A to point B, we can write that the gain in kinetic energy from A to B will be equal to loss in potential energy from B to A. Okay. You know that if we want to find the gain in kinetic energy, before this example I have told you an expression how to calculate the gain in kinetic energy. We can find 1 over 2 m into V square minus VA square. Okay, similarly the loss in potential energy will be equal to mg and change in height. Okay, now we can cancel these two quantities, and the velocity at point B will be 8 meters per second, because it is given that the greatest speed of this particle is 8 meters per second. So obviously the greatest speed of this particle will be at point B. So what we are going to do, VB is 8, it will become 8 square, and VA will be equal to 6.06 seconds. 6.06 seconds. Okay, and that will be equal to 2, and this G will come in denominator. If we simplify this, we will have the change in height of this body, and that will be equal to almost equal to 1.3 meters. Okay, now it's all about this example, and let's have another example. This is example 2. Okay. Okay, let's have another example. This is a body of mass 1250 kilogram. Let's suppose the mass of this body is 1250 kilogram, and this body is moving along this inclined plane, which is inclined at angle 7.2 degrees to this horizontal surface, and the length of this inclined surface is 400 meters. And it is given that this body is moving with constant velocity, and another information which is given is about friction, that the resistive force or the force of friction between this body and this inclined plane is 800 Newton, and we are supposed to find the work done by driving force or work done by this object when it moves from this point to this point. So we know that the work done by the driving force is equal to change in kinetic energy plus change in potential energy plus work done against friction. This is work done by driving force, and this is work done against friction. Okay, for potential energy we must have this height, and again using this trigonometric identity we can find this height. We know that sine 7.2 will be equal to h over 400. So h will be equal to 400 into sine 7.2. So that will be equal to 50 meters, almost 50 meters. So this height is basically 50 meters. Now we can see that the change in kinetic energy is basically equal to half mv square, half m into delta v square, change in velocity square, and the change in potential energy will be equal to mg into delta h, and the work done against friction is basically equal to the force of friction multiplied by the distance. Okay, we know that the velocity is constant, velocity is not changing. So if velocity is constant, it means there will be no change in velocity. So the change in kinetic energy will be 0. Okay, so one thing you need to remember, that if velocity is constant, then acceleration will be equal to 0 plus there will be no change in kinetic energy. Okay, now mgh we can substitute these values. Mass is 1250 and the change in height is 50 meters plus the force of friction is 800, and the distance covered from this point to this point will be 400. This is basically work done against friction, because the friction is 800 Newton between this object and this inclined surface. So if this body needs to overcome the friction, this body must apply 800 Newton force. So against friction, this body is applying 800 Newton force, and this force of 800 Newton is being applied for 400 meters. So the work done against friction will be equal to 800 multiplied by 400. Now if we multiply 1250 multiplied by 50 plus 800 multiplied by 400, we will have 3.8 multiplied by 10 raised to power 5 joules. This will be the work done against the driving force. And I think we have missed the value of G, this, because G is equal to 10, so 1250 multiplied by 10 multiplied by 50 plus 800 multiplied by 400. So we have 9.5 multiplied by 10 raised to power 5 joules. This will be the work done against friction. The work done for the driving force. Okay.